Hello and welcome to this online lecture. My name is Patty Kokish, and today we're going to be doing a final exam review for your online Math 136 class at Ivy Tech. What I'm going to do is I'm just going to pull problems from different sections and we're going to work on those. If you have any questions while we're going through this, you can use your control panel to go ahead and type the question. A little box will pop up for me so that I can see it right away. So feel free to ask questions if you have them, or if you want to wait till the end, that's fine as well. So we're going to start with polynomial functions and their graphs. So let's start with this example here, where we're finding a polynomial function from its zeros. So let's say that we know we have a polynomial with a degree of 3, and we know that the zeros are going to be -4, -2, and +3. So if we want to do this, degree of 3 is the highest power, okay, that we're going to have. And if you think about it, we have 3 zeros here, so it makes sense that we're going to have a degree of 3. So if we have -4 as one of the zeros, that means that x plus 4 has to be one of the factors, because when you take -4 and you plug it in to the equation here, x plus 4, this becomes a 0, exactly like you want it to. And since we know that -2 is also a 0, that means that x plus 2 is going to be a factor. And same thing with +3. So since we know +3 is a 0, it means that x minus 3 is going to be a factor. Now you'll notice here that we just have an a out front, okay? It really could be any real number that you want it to be. It could be a 1, it could be a 10, it doesn't really matter. You can choose whatever you'd like for it. Typically, what's done is you normally just let it be 1 because then it doesn't affect your equation and it just makes your life a little easier. So now what's done is make sure you pay attention to what MyMathLab says, because if it wants it in factored form, then you can just type it in just like this, but instead of a, you would just put the number 1, or you would just leave it out entirely. But if it wants it actually multiplied out, then you're going to have to actually FOIL the first two and then distribute whatever you have from this one to this. And you would get a times the quantity x cubed plus 3x squared minus 10x minus 24 if you were to go ahead and FOIL these two and then distribute an x through, and distribute a -3 through, then you would get this quantity right here. And then it says down here, a can be any real number. The easiest thing to do is just to let a equal 1. So in that case, into MyMathLab, you would just enter x cubed plus 3x squared minus 10x minus 24. One thing I want to point out before we move on is how you could check this to make sure that it's right. Now, this first one, there's really not a lot of checking to do, because if you plug -4 in, you know it's 0. If you plug -2 in, you know it's 0. If you plug 3 in, you know it's 0. So that's pretty easy. But down here, you want to make sure that you didn't make any silly kind of mathematical errors once you've multiplied it out. So what you could do is you could plug -4, -2, and +3 into your equation for your x and make sure that it still ends up being 0. And in this case, it should. When you actually do this, it will work because we multiplied it out correctly. But it will help you find any errors if you happen to make a mistake somewhere with your multiplication. Okay, now we're going to talk about the graph of a polynomial function. So a couple of things that are true about the graph of a polynomial. Well, we know that the degree is going to be n. We know that the graph is smooth and continuous. We should have at most n minus 1 turning points. And then we talked about multiplicity before. If you have even multiplicity, it means that the graph touches at the x-axis. If you have odd multiplicity, it means that the graph crosses at the x-axis. And then between the zeros, the graph is either going to be above or below your x-axis. And your end behavior is going to behave like the graph of your power function. So let's take a look at an example here. So let's say we want to analyze this graph here. So we have f of x equals 2x plus 1 times x minus 3 squared. So the first thing we want to do is determine the end behavior of our graph. So if you were to multiply this out, what you would see is that we're going to actually expand it to do this, okay? We would take x minus 3 and we'd square it, and we'd get x squared minus 6x plus 9, and we still have this 2x plus 1 here. And then we would go ahead and distribute the 2x to everything, distribute the 1 to everything. So we're left with 2x cubed minus 12x squared plus 18x plus x squared minus 6x plus 9. And then we go ahead and combine our like terms, so this looks a little nicer. So we have 2x cubed minus 11x squared plus 12x plus 9. So if you look at this, the first term determines your end behavior if you've written them in descending order. So our first term is just 2x cubed. So that means that our graph is going to behave just like y equals 2x cubed for any large values of x. Now, one thing that I want to point out, it was fine that we multiplied this all out, but we did not really have to do all of that work. If we go back to the original function for a minute, we know that we have a 2x here, and we know that when we multiply this out, we're going to get an x squared. So if you have 2x multiplied by x squared, that means that your first term that you're going to end up with will be 2x cubed, because you have an x from here and an x squared from here, which would come together to form an x cubed, and you still have this 2 out front. So it's not completely necessary that you multiply this entire thing out to find the power function, but what you want to do is think about when you are to multiply this out, what would your leading coefficient and your highest power be, and that would be 2x to the third power. Okay, now we want to find the x and the y-intercepts. So the y-intercept is going to be found by taking x and setting it equal to 0. So if you go ahead and try, if you take x and you set it equal to 0, you have 2 times 0 plus 1. That's just going to be 1. And then you have 0 minus 3 squared. 0 minus 3 is going to be negative 3. Negative 3 squared is going to give you a positive 9. So you have 1 times 9, which gives you 9. So that's your y-intercept. And then to find the x-intercepts, we set y equal to 0. So we have 0 equals 2x plus 1 times x minus 3 squared. And then we use the zero product property and we set each piece equal to 0. So we know that either 2x plus 1 is equal to 0 or x minus 3 squared has to be equal to 0. And then we just solve each of these. Over here, we're going to get x equals negative 1/2 from this one. We subtract 1 and divide by 2. And over here, we take the square root of both sides, so we get x minus 3 equals 0. And then we get x equals positive 3. So we know that our x-intercepts are going to be at negative 1/2 and 3. Now, be careful with your x and your y-intercepts in MyMathLab. Make sure that you pay attention to whether they want a coordinate or just a number. So if they want the coordinate, for the y-intercept, you'd put 0, 9, and for the x-intercepts, you'd put negative 1/2, 0, and 3, 0. But if they just want the points, then you would just type the numbers. Now, step 3 is to determine the zeros of the function and their multiplicity. So we already found the 0 of negative 1/2, and if you look back to the original function, this was the piece that gave us the negative 1/2. Now, all you have to do is look at the power, okay? So the highest power of x that we have is just the first power. So that means that it has a multiplicity of 1. Anytime you have an odd multiplicity, so 1 is an odd number, that means that your graph is going to cross there. Now, if we take a look at this 0, we know that we have a 0 of 3. If you look at the multiplicity, we have a power of 2. That's an even number, so that means that the graph touches there. If you just remember ET, even touches, so if you remember the movie ET, even touches, that should be enough to remember all of the things that deal with multiplicity. So you know if you have an even multiplicity, it's going to touch. Odd multiplicity is just cross by kind of default. And then step 4 is to determine the maximum number of turning points. So we know that the polynomial is a degree of 3, so that means that the graph can turn at most 2 times. And then we want to determine the behavior of the graph near each of the x-intercepts. I would say that this is the least important of the steps. You can still draw a pretty good graph without doing this, okay? So if you look at near negative 1/2, we know that's one of our zeros. What we do is we take negative 1/2 and we plug it in to the factors that did not make that 0. So we can't plug it in here to the 2x plus 1 because it's just going to make it 0. So we leave this piece intact, and then we plug negative 1/2 in for the other x values. And then if you actually multiply this through and simplify, you get 25 over 2x plus 25 over 4. We know that that's just a line that has a slope of 25 over 2. And then near 3, we look back at our original equation. We can't plug 3 into this factor because we know it's just going to make it 0, so we plug 3 in over here. So we have 2 times 3 plus 1 times the quantity x minus 3 squared, which is going to be 7 times the quantity x minus 3 squared. We know that that's a parabola that opens upward. And again, I would say that this is the least important part of drawing the graph of a polynomial, because you can still get a pretty good graph without actually knowing what this behavior is near the x-intercepts. So let's put all of this information together. So the first thing that I want you guys to do when you're thinking about drawing a polynomial is to put all of the intercepts on, okay? So we put a 3, 0, on our graph. We put -1/2, 0, because those were our x-intercepts, and then we also put a y-intercept at 0, 9. So I would suggest doing that first, so you have your 3 points here. And then what I would suggest doing next is drawing your end behavior. Okay, so we know that the graph resembles the equation 2x cubed. And if you think about what 2x cubed is going to look like, that's just going to look like x cubed on the ends. We know that x cubed is kind of the sideways S shape where it goes up on the right and down on the left. So what you're going to want to do is from these zeros, you're going to want to draw something that's going up on the right. And from over here, you're going to want to draw something that's going down on the left. So then all we have to do is figure out how to connect these dots here. And you can do that one of two ways. You can either use the multiplicity, which is the touch and cross thing, or you can use the behavior near the intercepts. Now, my suggestion would be to just think about the cross and the touch. So we know that at -1/2, our graph is actually going to cross the x-axis. So that means that I have to go through it here. And that makes sense because I have to get up to this point somehow, okay? So I'm going to draw my line actually through this, and then I have my y-intercept, and then at some point I have to work my way back down here. And then at 3, 0, we know that our graph is just going to touch the x-axis, so that means here I touch and I just go back up in this other direction. So if you look at the nice smooth line we've drawn, it looks something like this. And you'll see that they found a couple of other points, 1, 12, 4, 9, and -1, -16. These just kind of confirm that you've drawn the correct graph. This is always a good idea if you have some extra time to go ahead and pick a couple of extra points and make sure that they actually fit with the picture that you have drawn. Okay, now let's take a look at rational functions and their graphs. So this was the other big graphing thing that we did in this half of the semester. So first I want to talk about how you find a horizontal or an oblique asymptote of a rational function. So if you look at this rational function here, we're going to call the degree of the numerator n and the degree of the denominator m. Okay, so we have n up top, m down below. So if n is less than m, which means the degree of the numerator is less than the degree of the denominator, then r is said to be a proper rational function. And the graph is going to just have a horizontal asymptote, which is the line y = 0, which would just be your x-axis. So that's kind of your nicest case. So if the degree of the numerator is less than the degree of the denominator, then it's just y = 0. Now, if the degree of the numerator is greater than or equal to the degree of the denominator, then r is considered improper. So we have to use some kind of information here. So if the two are the same, so if the two degrees are equal, so if n is equal to m, meaning the degree of the numerator is equal to the degree of the denominator, then all you have to do is take the leading coefficient in your numerator and divide it by the leading coefficient in your denominator. And that gives you your horizontal asymptote. So you just have y = a sub n over b sub m. So it's just going to be the number in the numerator divided by the number in the denominator. And that's going to give you your horizontal asymptote. Now, if the degree of the numerator is 1 more than the degree of the denominator, then what you have to do is you have to actually do long division or synthetic division in order to get the quotient. And it's going to have an oblique asymptote that you're going to find by actually dividing. Now, if the degree of the numerator is 2 or more greater than the degree of the denominator, then the quotient is going to be some polynomial of degree 2 or higher. So r is considered to neither have a horizontal nor an oblique asymptote. But in this case, for very large values of x, the graph is going to behave like the graph of the quotient. But that's going to be kind of a little more complicated, and it's not actually a horizontal or an oblique asymptote. So let's take a look at this example here. So we have r of x equals 8x squared minus x plus 2 over 4x squared minus 1. So what you want to pay attention to when you're trying to find the asymptotes is the degree of the numerator and the degree of the denominator. So we know that the degree of the numerator is 2 because that's the highest power that we have here. We know that the degree of the denominator is also 2. So if the degrees are the same, all we have to do is look at the leading coefficients. So if you look at the leading coefficient up here, it's 8. The leading coefficient down here is 4. So all we have to do is say that y equals 8 over 4. And then we would simplify this to y equals 2. So that's going to be our horizontal asymptote in this case. Now, we have a way of analyzing graphs of functions which involve a bunch of steps. What we just did is one of the steps, but let's take a look at all of them together, and then let's go ahead and do an example. So step 1 is to always factor the numerator and the denominator, and then find the domain. Step 2 would be to write your rational function in lowest terms. Step 3 would be to locate any intercepts that you have. So the x-intercepts are going to be the zeros of the numerator, and then you determine the behavior of the graph near each of the x-intercepts. Step 4 is to determine the vertical asymptote, and then you graph each vertical asymptote using a dashed line. Step 5 is to determine the horizontal or oblique asymptotes if one exists. That was what we just did. And then once you have those, you also want to graph that with a dashed line. Step 6 is to use the zeros of the numerator and zeros of the denominator to divide the x-axis into intervals. And then what you do is you just determine where your graph is above or below the x-axis by choosing a number that's in the interval and evaluating. And then you can plot the points that are actually found there. And then you analyze the behavior of the graph near each of the asymptotes and indicate this behavior. And then once you put all of that together, you have a fairly nice graph of your rational function. So let's take a look at this example here. So we have r of x equals x minus 1 over x squared minus 4. So the first thing we want to do is we want to factor the numerator and factor the denominator, and then go ahead and find the domain. Now, if there is something that cancels, you do not cancel it yet, okay? You have to find the domain first. So if you notice, our denominator factors into x plus 2 times x minus 2. Our numerator, there's nothing we can do with that. So this is our factored rational function here. Now the domain is going to be all numbers x such that x is not equal to negative 2 and x is not equal to positive 2. Because if x is equal to negative 2, it makes our denominator 0. And if x is equal to positive 2, it also makes our denominator equal to 0. So we have to exclude those 2 points. Now we want to write r in lowest terms, and if you notice, there are not any common factors between the numerator and the denominator, so r is already in lowest terms, so there's no canceling to do. But if there were canceling to do, you would do it after step 1. Step 3 is to locate the intercepts. So since 0 is in the domain, the y-intercept is going to be found by just plugging 0 in for x. So if we plug 0 in for x, we can either look at our factored version or our original. I think the original is a little easier to look at, but if we plug 0 in here, we get 0 minus 1 over 0 squared minus 4. That's just going to be negative 1 over negative 4, which is going to simplify to 1/4. So we know that that's our y-intercept. And then to find the x-intercepts, we set the numerator equal to 0. So all we have to do is set x minus 1 equal to 0, and we would get x equals 1. So that's going to be our x-intercept, and that's the only x-intercept that we have. Now near 1, in order to find that behavior, we do the same thing that we did with polynomials. We can't actually plug 1 into our numerator because it would just make it 0, but what we can do is we can plug 1 in to our denominator x's. So we have 1 plus 2 times 1 minus 2 in our denominator, and we still have this x minus 1 up top. This is going to simplify, and we have negative 1/3 times x minus 1, which we know is just going to be a line, okay, with a slope of negative 1/3. Now we want to locate any vertical asymptotes that we have. So vertical asymptotes happen where your denominator is equal to 0. So if we take a look back at our factored form, we have x plus 2 times x minus 2 in our denominator. If we were to set that equal to 0, we would get two lines at x equals negative 2 and x equals positive 2. Those are the equations of our vertical asymptotes. Now, if you think about the horizontal or oblique asymptotes, this is where you need to pay attention to the degrees. So we know that the degree of the numerator is 1 and the degree of the denominator is 2. So we know that our degree of our numerator is less than the degree of the denominator. That means that our irrational function is proper, so the line y equals 0 is going to be the horizontal asymptote. Now, in order to determine if the graph of r intersects the horizontal asymptote, we would have to set r of x equal to 0. So let's take a look here at what we have so far. So we have a vertical asymptote at x equals negative 2, a vertical asymptote at x equals 2, and then we have a horizontal asymptote at the line y equals 0. Now, if we actually plug 0 in for our value of y, we're going to get one solution here of 1, 0. And we know that this is the case because this is our actual x-intercept. So we have an x-intercept of 1, 0 and a y-intercept of 0, 1/4. So we know that this piece is going to go through these 2 points. Now what we need to do is we need to pick some additional points because it's too difficult to see where the other pieces are. We could have a piece up here or a piece down here. This could look something like this, or it could just be more parabola shape, and we're going to have something over here as well. So in order to figure out what all of that looks like, you want to go ahead and take a number line and divide it based on your intercepts and your asymptotes for x. So we know that we have an asymptote at negative 2 and 2, and we know that we have an x-intercept at 1. So that's how we divide our number line. So we have an interval from negative infinity up to negative 2, and then another interval from negative 2 to 1, from 1 to 2, and then from 2 to infinity. And then what you need to do is you need to pick a value that's in each of those intervals. So if you think about an interval from negative infinity to negative 2, we could pick the number negative 3 as our actual value. We could pick 0 in this interval, 3 halves in here. There aren't any nice numbers that live between these two. 1.5 is the nicest. And then 3 over here. And what we've done is we've just taken these values and we've substituted them back either into the original equation or into our factored equation. And if you plug negative 3 in, you get negative 0.8 out for y. If you plug 0 in, you get 1/4 out. If you plug 3 halves in, you get negative 2/7 out. And if you plug 3 in, you get 0.4 out. And really what you want to pay attention to, these points are nice to have as well, but you want to pay attention to the signs. So if you have a negative number here, that means that we're going to be below our x-axis. Same thing over here. But here, and in this last piece, we had positive numbers. That means we're going to be above our x-axis. So let's take a look at this and let's put all this information together. So we have what we had before, okay, but we also have some additional points. We have a point at negative 3 and a negative 0.8, a point at 3 and 0.4, and then a point down here as well that we found. And if we take a look at this, if we determine where things are above and below the x-axis, we know that from negative infinity up to negative 2, we're going to be below our axis. And we know it goes through this point, so it has to look something like this over here. Over here, from 2 to infinity, we know that we're going to be above our x-axis because we have a positive value. So it's going to look something like this. And then we know over here that we're going to be below our x-axis from 1 to 2. So we know that we're going to have some piece up here, or sorry, down here. And then we know that from negative 2 all the way up to 1, we're going to be above our x-axis. So that means that we have to have a piece that looks something like this. Step 7 was shown here as well, and you can figure out what these various things look like near the asymptotes, but it's actually not necessary. Once you figure out whether something is above or below the axis, you can draw a pretty good picture just from that. So this really gives you all of the information that you need without doing step 7. Okay, let's take a look at polynomial and rational inequalities for a minute. So let's say that we want to solve this inequality here. X to the fourth is greater than x, and then we want to go ahead and graph the solution set. So I think that the easiest way to do this is algebraically. Your textbook shows you how to do it graphically and algebraically. I personally think that the algebraic method is a lot easier, especially since you're already doing so many different graphs. Students tend to get a little bit tired of graphs. So let's take a look at how to do this algebraically. So the first step is to write the inequality so that the polynomial is on the left side and we have a 0 on the right-hand side. So we set this equal to 0 over here. So we just subtract x from both sides. So we get x to the fourth minus x is greater than 0. And then we determine the real zeros, or the x-intercepts of the graph. So what we need to do is we need to factor this. So this is going to factor the following way. So we're going to take an x out of both of these because we have a greatest common factor of x. And we're left with x times the quantity x cubed minus 1. And we're setting this equal to 0 in order to find the real zeros. Now x cubed minus 1 is just the difference of two cubes, so this should factor this way. So we should be left with this x out front still, and then we have x minus 1 times the quantity x squared plus x plus 1 equals 0. And then what we do is we set each of the pieces equal to 0 using our zero product property. So we know that either x equals 0, x minus 1 equals 0, or this quadratic that we have here, x squared plus x plus 1 equals 0. And if we solve each of these, we get x equals 0 or x equals 1. We're not going to have any real solutions for this one. So then what we do is we use the zeros that we found in step 2 in order to divide a number line. So this is a lot like what we did in the last rational graph question. So we know that we have a 0 at 0 and a 0 at 1. So our intervals are going to be from negative infinity up to 0, and then we're going to have another interval from 0 up to 1, and then a third interval from 1 to infinity. So what we do is we just take our number line and we divide it that way that we just talked about. So from negative infinity up to 0, 0 to 1, and 1 to infinity. And just like last time, we actually pick a value in each of these intervals and then solve it. So negative 1 is going to be in this interval over here, 1/2 is going to be over here, and 2 is going to be over here. Now, what you want to do is you want to substitute this back into this equation here, either your factored equation that you have here or the one where you have a 0 on the right hand side, but you don't want to substitute it back into the original, okay? So if you take negative 1 and you plug it in back to our factored version, you're going to get a positive 2 out. If you take 1/2 and you plug it in, you're going to get negative 7 over 16. And if you take 2 and you plug it in, you're going to get a 14. Now, we don't actually care about these values at all. All we care about is if it's positive or negative. So this one is positive because 2 is a positive number. 14 is also positive, and then in the middle we have a negative. Now, oftentimes this is the case where you're going to get something where the signs kind of flip-flop, okay? So that's kind of a good indication that you probably did it correctly. Now, it's always possible to get different patterns, so make sure that you double-check these. What you can do to kind of confirm that you're correct is to pick an additional number that's in the interval and make sure that you have the same conclusion here. Now what we want to know is we want to know where f of x is positive because we had a greater than sign. So what we care about is our actual positive solutions. So our intervals are going to be from negative infinity to 0 and then from 1 to infinity because that is where we had a positive solution. That's one way you could write it. The other way is back over here, our set builder notation. We could write it x such that x is less than 0 or x is greater than 1. Either one of these is fine, but make sure that you pay attention to whether MyMathLab wants interval notation or set builder notation. Now, if we had had this same problem but with a less than sign, then what we would have done is we would have taken the negative solution instead, and our interval would have been from 0 to 1. And then if we're talking about graphing our solution set, it's going to be from negative infinity up to 0, not including 0, because we have strictly greater than, not greater than or equal to. And then we have from 1 to infinity, again, not including 1, because we have strictly greater than, not greater than or equal to. All right, let's take a look at one where it's a rational inequality. Now this one I picked kind of a tricky one, okay, so we have to do quite a bit of thinking here before we can actually solve this. But what we want to do first is we want to write it so that we have 0 on the right-hand side and the rational expression on the left. So you'll see that we need to subtract 3 from both sides in order to do that. So we have 4x plus 5 over x plus 2 minus 3 is greater than or equal to 0. And then with the rational inequalities, what you need to do is you need to simplify this. You need to make this look a little nicer. So we have to get a common denominator, which is going to be x plus 2. So what we need to do with our negative 3 here is we need to multiply it by x plus 2 over x plus 2. This will ensure that we haven't changed our expression at all, but we're just going to get it so that it has a nice common denominator. So if we actually do this, if we multiply this through, we're going to be left with 4x plus 5 from up here, and then we're going to have negative 3x minus 6 in my numerator, and now I have everything over the quantity x plus 2. And then what I want to do is just combine like terms. So 4x minus 3x gives me a positive x. Positive 5 minus 6 gives me a negative 1. So I'm left with x minus 1 over x plus 2 is greater than or equal to 0. Now this looks much nicer than my original because I have 0 on the right-hand side and I have everything as a part of one fraction. So there's nothing really that I need to do there. Okay, now I just have to go about solving my equation. So now what I need to do is I need to determine the real zeros and the real numbers for which f is undefined. So all you need to do when you have a rational inequality like this is you need to set your numerator equal to 0 and you need to set your denominator equal to 0. So if I set x minus 1 equal to 0, I'm going to get x equals 1 as my 0 of my numerator. And if I set x plus 2 equal to 0, I'm going to get x equals negative 2 as my 0 of my denominator. So 1 is an actual 0, negative 2 is where my function is undefined. And what these help me do is to create intervals. So I'm going to have an interval from negative infinity up to negative 2, because that's my first point that I come across. And then I'm going to have an interval from negative 2 up to 1, and then a last interval from 1 to infinity. So all I need to do is I need to take my number line and divide it, and then I pick a number in each of the intervals. So again, I'm going to pick negative 3 here, 0, and 2. And then what I do is I plug them into my nice simplified version of my equation. So I would plug them into this equation right here, x minus 2 over x plus 2. And if you do this, you get 4 out when you plug negative 3 in, you get negative 1/2 out when you plug 0 in, and you get 1/4 out when you plug 2 in. And again, I don't really care what these values are. All I care about is the signs. So I have a positive number here, a negative number here, and a positive number here. Now this one is particularly tricky because we care about greater than or equal to. So I know that I don't care about my negative solution because I don't want less than. But I need to be careful about how I write my actual solution. So I know that I'm going to have numbers from negative infinity to negative 2 and from 1 to infinity, but I need to figure out where I have brackets and where I have parentheses because I have this equal to piece. So if you think about the actual number negative 2, you want to decide if we should actually include that in our solution. So if you take negative 2 and you plug it back into our nice little equation that was all simplified, what you'll find is that you get a 0 in the denominator. Now we're never allowed to have 0 in the denominator, so that means that we have to have a parenthesis at negative 2, meaning that we cannot actually include negative 2 as part of our solution. Now for this other one, from 1 to infinity, if I plug 1 into my equation, I just get 0 in my numerator. Now 0 is fine to have in the numerator, so that means that I actually want to include the number 1. So I put a bracket there. So my final solution using interval notation would be from negative infinity up to negative 2, union 1 to infinity, but with a bracket next to the 1 because we're including it. Or you could write it in set builder notation, which is on the left here, x such that x is less than negative 2 or x is greater than or equal to 1. So make sure that when you're doing anything where you have a greater than or equal to or less than or equal to with a rational function, that you're paying a lot of attention to which endpoints you should actually include and which ones you should exclude. And if you look at the number line here, it's shown as well, negative infinity up to negative 2, and then 1 to infinity, but actually with a bracket at 1, including that number. Okay, now let's do a quick review of complex zeros. So this should be an easy concept once you remember this, but this is something that I think is easy for students to forget. So let's say that we have a polynomial of degree 5 whose coefficients are real numbers, and we know that it has the zeros negative 2, negative 3i, and 2 plus 4i. And what we want to do is we want to find the remaining 2 zeros. So hopefully you remember that conjugate pairs or conjugate numbers come in pairs. So if we have negative 3i as one of our zeros, it means that positive 3i also has to be a zero. So f has coefficients that are real numbers. Complex zero appears as conjugate pairs. And this is always going to be the case if you have a function where we have coefficients that are real numbers. So since we have negative 3i, the conjugate pair is going to be a positive 3i. And then since we have 2 plus 4i, our conjugate pair is going to be 2 minus 4i. So those are the two remaining zeros, just a positive 3i and a 2 minus 4i. So I told you that was going to be a little quick review. If this doesn't look familiar to you, what I would go back and do is watch the lecture where we covered complex zeros, and particularly to go back and look at the conjugate pairs theorem. Okay, let's take a look at composite functions. So let's suppose that we have two functions here. We have f of x equals 2x squared plus 3, and we have g of x equals 4x cubed plus 1. And what we want to do is we want to evaluate several different composite functions. So for part A, I want to find f of g of 1. So that means that I want to take g of 1, which is on the inside, and I want to plug it into f. So the first thing that I need to do is I need to actually figure out what g of 1 is. So that means that I should go ahead and find it. So all I need to do is I need to plug 1 into my g of x function. So I have 4 times 1 cubed plus 1. And if I actually do this, that's just going to give me a 5 out. So what I'm really finding is f of 5. And now all I have to do is take my f of x function and plug 5 in. So I have 2 times 5 squared plus 3, which is going to give me 53 here. So that would be my solution for f of g of 1. Let's do another one. Let's do g of f of 1. So now I'm going to find f of 1 first. So I'm going to plug 1 into my f of x function. So I have 2 times 1 squared plus 3. That's going to give me a solution of 5. And then I'm just going to plug that into my g function. So I have g of 5. So I take 4 times 5 cubed plus 1. That gives me 501. All right, now what I want you to do is I want you to go ahead and try one of these. So we have f of negative 2. So that means that you're going to take f of negative 2, you're going to figure out what that is, and then you're going to plug it back into f. So I want to give you about a whole minute to try that one. And if you're done with that, you could go ahead and try d, which I'm going to put up on the screen in just a minute. So I'm going to put some of the steps up here. So f of negative 2 should be 11 when you plug it in. So what you're going to find next is f of 11. So double check, make sure that you're able to get the 245 here. And then once you have that, I want you to go ahead and find g of negative 1. So that means you're going to find g of negative 1 first, you're going to evaluate that, and then you're going to plug it back into your g of x function. Okay, so g of negative 1 should end up being negative 3 when you solve it. So if you plug negative 1 into your g of x function, you should get negative 3 out. And then you're going to take that negative 3 and plug it back into g. So you have g of negative 3. And hopefully you were able to get negative 107 when you actually plug negative 3 into your function here. Okay, so let's take a look at inverse functions. So let's take a look at a graph first, and then I think we're going to do one with an equation as well. I think I have one of those next. So we have a graph of a function that's 1 to 1, okay, meaning that it passes our horizontal line test, so we can move our horizontal line through and it passes. And we want to go ahead and draw the inverse. Now the easiest way to think about this is to just flip-flop our coordinates. So we know that if we have negative 2, negative 1 on our original graph, then we're going to have negative 1, negative 2 on our new nice little pink graph here. If we have negative 1, 0, that means we're going to have 0, negative 1. So all we're doing is we're flip-flopping our x and our y coordinates. And then if we have 2, 1, we know we're going to have 1, 2. So we have these 3 points here, and if we just connect our nice little dots, we'll have the inverse function. Now, the other thing that you can notice is on the graph of the inverse, there's this line y equals x. So this is just a line that creates a 45-degree angle with your axis. It goes right through your origin. And if you imagine taking this blue line and flipping it across the line y equals x, you would end up with this pink line here, which is just another way to find your inverse. So that works as well. Whatever makes more sense. But just keep in mind, all you're doing is you're flipping your x and your y coordinates, and you're just recreating your graph. Now, it looks like I don't have an example of that. I think maybe I have one in this section where we find the inverse. If not, I would make sure that you go back and you review that section where you find inverses algebraically. So let's take a look at some exponential equations here. So we have 2 to the power 3x minus 1 equals 32, and we want to solve this. So the first thing that you want to try to do is to see if you can get the same bases. So we can rewrite 32 as 2 to some power. So if you think about it, 2 squared is 4, 2 cubed is 8, 2 to the 4th is 16, and 2 to the 5th is 32. So all I'm going to do is I'm going to rewrite 32 as 2 to the 5th power. Now that we have the same bases here, what you can essentially do is just ignore the bases and keep the exponents. So what you can say is that 3x minus 1 has to equal 5. And then all you need to do is solve this, and you'll get x equals 2 if you add 1 to both sides and then divide by 3. So now that you have x equals 2, what you're going to do to check it would be to take 2, plug it into the original, and make sure that it works. And what you'll get is 2 to the 6 minus 1 power, so that's 2 to the 5th power. And you can double check that in your calculator, but that should give you 32. Now this one over here, you have a lot of e's, but what you want to do is you just want to try to write it kind of in a nicer way. So all we've done from this first to the second step is to take this and to put it in my numerator here. And then the other thing you'll notice is if you have a power to a power, all you're doing is you're multiplying those numbers. So I left e to the 2x minus 1 alone, and then all I've done here is I've rewritten this as e to the negative 4x power over e to the 3x. And then if you take a look at this right-hand side, since we have the same bases, when you have division, hopefully you remember that you can subtract the exponents. So if you take negative 4x and you subtract 3x, you're going to be left with a negative 7x. So we know that e to the 2x minus 1 power is equal to e to the negative 7x. Now that we have the same bases on both sides, we can ignore those bases and just set the exponents equal to each other. So we have 2x minus 1 equals negative 7x. And then we just subtract 2x from both sides and divide by negative 9. So we get x equals 1/9. This one is not as easy to check, but it will work the same way as the other one if you go back and you plug it in to the left-hand side and to the right-hand side. You'll get the same solution for both. Now, here's a whole nice little summary of the properties of your logarithms. So I would make sure that you're comfortable with these, or double check the formula sheet to see what exactly is provided, so that you're going into your final exam fully prepared for what you're given. So I'm not going to go through all of these, but a couple of big ones that I want to point out is this one right here in particular. If you have log base a of m to the r power, what you can do with exponents is that you can make them factors. So you can take this r and you can move it out front. So hopefully you remember this from when we did logarithms. In addition, if you have something that's multiplied, you can expand it so that it's addition. And if you have division, you can expand it so that it's subtraction. And then another big thing is being able to rewrite from logarithmic to exponential form. So if you have y equals log base a of x, that means that x equals a to the y power. It is very important that you're familiar with this concept here, because many times in order to solve an equation, you'll have to kind of go between the two different types of equations. So let's take a look at that. That's these examples here. So we want to change an exponential expression into a logarithm. So we have 1.2 cubed equals m, and what we want to do is we want to rewrite it with a logarithm. So if you take a look at how this formula is kind of comprised here, 1.2 is our base, okay? So that means that it's going to be our base down here. Now the number m is by itself, so it's going to become attached to our logarithm. So really what this is going to be is log base 1.2 of m equals 3, okay? So again, we have log of our base, so we have log base, whatever our base was, so we have log base 1.2 of m is equal to 3, which was our exponent. So I want to give you about 30 seconds. I want to see if you can rewrite B and C, and then I'm going to put the answers up. Okay, so hopefully for B, you were able to figure out that it should be B equals log base E of 9. Now, one thing that I want to point out, log base E is not wrong, but log base E is the same as natural log. So you could have also written this as B equals ln of 9, and that would have been fine as well. And then for C, you should get 4 equals log base A of 24. Again, if you're not comfortable with this, I would make sure that you go back and look at the exponential and logarithmic videos. Okay, now let's take a look at your change of base formula. This is not one of the ones that I pointed out, but hopefully you remember. If you have log base 5 of 89, what you do is you take log of 89, which is the physically larger number, not 5 versus 89, but the one that's actually written largely. Okay, so the 89 is in kind of full font, the 5 is tiny, right? So you take log of 89 and then you divide it by log of your base, which is 5 in this case. So you have log of 89 over log of 5. Alternately, you could do ln of 89 over ln of 5. You just need to make sure that you're consistent. If you use log of 89, you have to use log of 5. If you use ln of 5, you have to use ln of 89. So you have to use the same one right here. And if you do either of these, you should get 2.7889. Now I want to give you about 15-20 seconds to see if you can get this one over here. This is not any nastier, it just has numbers that aren't as nice, but I want you to see if you can figure out what log base square root of 2 of square root of 5 is. So this should be log of square root of 5 over log of square root of 2. Now, you could also do ln of square root of 5 over ln of square root of 2. Again, it does not really matter. And you can plug this in your calculator just how it is, or what you could remember is that square root is the same thing as the 1/2 power. And since you have this 1/2 power, you move it out so that it's a factor of 1/2 times log of 5 over 1/2 log of 2. The 1/2s are going to cancel, so you're really just left with log of 5 over log of 2. Now that would be a nice way to simplify this, okay? But if you just want an approximation, you could plug this into your calculator as well, and you'll get 2.3219. Okay, now let's take a look at how to expand something. So we have log base 2 of the quantity x squared times the cube root of x minus 1. And we're told that x is greater than 1. Now the reason for that is so that we don't end up with a negative logarithm, but we want to rewrite it as a sum of logarithms. So if you notice, x squared and cube root of x minus 1, these two things are being multiplied. Anytime we have multiplication, we can split it into two different logarithms as long as we make it addition. So really what we have is log base 2 of x squared plus log base 2 of cube root of x minus 1. Now the next thing you'll notice is that we can rewrite our cube root as the 1/3 power. So we've taken log base 2 of x squared, we leave it alone for right now, and then we've rewritten the cube root as log base 2 of x minus 1 to the 1/3 power. And then what we can do is we can take both of our powers, we have x squared here and x minus 1 to the 1/3 power, and we can bring those powers out front. So really what I have is 2 times log base 2 of x plus 1/3 times log base 2 of x minus 1. Now there are no more exponents, there are no more roots, and there's no more multiplication or division left in here. So this is kind of as far as I can take this one. All right, let's try one that has division in it. So we have log base 6 of x to the fourth over x squared plus 3 squared, where x is not equal to 0. So the first thing that you should notice is that we have a division problem. So what we're going to do is we're going to change it into subtraction. So we have log base 6 of x to the fourth, that was my numerator, minus log base 6 of x squared plus 3 squared, that was my denominator. And then what I want to do is I want to take my powers, my exponents, and I want to change them into factors. So I take my 4 and I stick it out front here. So I'm left with 4 times log base 6 of x. And then I take my 2 that I had as a power and I write it as a factor as well. So I have minus 2 times log base 6 of x squared plus 3. And again, I don't have any multiplication or division left, so I'm done. All right, let's try this one here. We have ln of x cubed times the square root of x minus 2 over x plus 1 squared. So I'm going to give you a minute, see if you can figure out how to write this as the sum and difference of logarithms. If you're stuck, my first suggestion would be to change it into subtraction because of the fact that you have division. So I'd give that a try. I'm going to give you about 30 more seconds to see if you can figure out the first step. Okay, so hopefully you were able to figure out that you can change this into subtraction. So we have ln of x cubed times the square root of x minus 2 minus ln of x plus 1 squared. And then what I want you to do is figure out how you could simplify this first piece, because if you look here, you have these two things which are being multiplied. So I want you to go ahead and see if you can rewrite those from multiplication into addition. So hopefully you are able to split this up. This should be ln of x cubed plus ln of x minus 2 to the 1/2 power. So the other thing that they've done in this step is they've taken the square root, and instead of writing it as the square root, they've written it as the 1/2 power. These two things are equivalent, but this one's a little nicer because now it has a power which we can change into a factor. So the last step I want you to do is I want you to take your powers and I want you to make them factors. So I want you to move them out front of each of their respective pieces. So let me give you a couple of seconds to try that. So you should get 3 times ln of x plus 1/2 times ln of x minus 2 minus 2 times ln of x plus 1. Now there are no more exponents, there are no more roots, there's no more multiplication or division within each of these little ln's. So that means that we are done at this point. Okay, now let's do it in the opposite direction. So let's go ahead and take something that is already expanded and then write it as a single logarithm. So let's do a and b together, and then I'm going to let you guys try c. So for a, we have 3 times ln of 2 plus ln of x squared. Now you notice that these are added together, so we know we're going to change it into multiplication. But what we actually want to do first is we want to take any numbers that are out front and we want to make them into exponents. So for this one, we've taken this 3 that's out front and we've rewritten it as an exponent. So we have ln of 2 cubed plus ln of x squared. And then what we're going to do is we're going to go ahead and change these so that it's multiplication. And you'll notice 2 cubed, hopefully you know that's 8, okay? So really what we have is ln of 8x squared. Now we've changed this back into multiplication because it was addition. Now this one here, we're going to do the same kind of thing. First thing we're going to do is we're going to take our factors and we're going to rewrite them as powers. So we're going to move them back up here. So we've rewritten this as log base a of 4 to the 1/2 power minus log base a of 5 squared. So we took this 2 and we moved it up to a power. We took the 1/2 and we moved it up to a power. And then since we have subtraction, we're going to change this into division. And then the other thing that I want to point out is that we can simplify this a little bit. So 4 to the 1/2 power is just going to be the square root of 4, which is just 2. And 5 squared is just 25. So since we have subtraction, we changed it into division. So I'm just left with log base A of 2, since 4 to the 1/2 power is 2, over 25, since 5 squared is 25. So let me give you about a minute to see if you can figure out how to do this last one here. So hopefully you have this first step that I'm going to put up here, which is where you take the factors that are out front and you move them up so that they're exponents. Once you have that, you can simplify this a little bit. You can rewrite this piece right here as multiplication. And then probably what you want to do is you actually want to figure out what 2 cubed times 3 to the negative second power is. Because 2 cubed is going to give you 8. 3 to the negative second power is going to give you 1/9. And then since you have subtraction, you want to go ahead and rewrite it as division. So hopefully you were able to figure out that this piece, this x squared plus 1, should be in your denominator because it's subtracted. And then 2 cubed is 8. 3 to the negative second power is 1/9. So the nicest thing to do is to take your 9 and to actually stick it in the denominator with your x squared plus 1. Okay, now let's take a look at solving a logarithmic equation. So we have log base 3 of 4 equals 2 times log base 3 of x. So what we would like to do is hopefully get it so that we have just log base 3 of something and log base 3 of something. And then what we can do is we can ignore the log base 3's and just solve. So hopefully you've noticed here, if you have this 2 out front, we can move that up so that it's a power. So we have log base 3 of 4 equals log base 3 of x squared. So what we do is we set 4 equal to x squared, and then this is something that we can solve. Now we're able to do this because we have a log base 3 on the left-hand side, we have a log base 3 on the right-hand side, and they're both alone. Since they're both alone, we can just kind of ignore them, and we're just left with 4 equals x squared. Now in order to solve this, you would take square root of both sides. So we'd get x equals 2 or x equals negative 2. Now it's really important that you check this in the original logarithmic function because we cannot have negative numbers inside of our logarithm. So the domain of logarithmic functions is only positive numbers. So we have to be careful and check for extraneous solutions. So if we take x equals 2 and plug it in here, this is going to be fine because we just have log base 3 of 2. There's nothing wrong with that. But if we take negative 2 and we plug it in, we'd have log base 3 of negative 2. That is not going to be good because we cannot have a logarithm of a negative number. So that one right there is going to be extraneous. So we're just left with x equals 2 as our solution. All right, let's take a look at this one here. So we have log base 2 of x plus 2 plus log base 2 of 1 minus x equals 1. So the first thing that hopefully you notice is that these two logarithms have been added together. So what we can do is we can change it into multiplication. So we have log base 2 of x plus 2 times 1 minus x equals 1. And then what you'll notice is that we can just change this into exponential form. So this 2 becomes our base. This 1 becomes our exponent. So really right here we have 2 to the first power equals x plus 2 times 1 minus x. And again, this is using that equation that I said is very important from changing from logarithms into exponential and the other way around. And then if we just go ahead and factor this and solve, when we FOIL this, we're going to get negative x squared minus x plus 2, and then we still have equals 2. We're going to move everything so that it's on the left-hand side so that we have 0 on the right. So we're left with a positive x squared plus x. The 2's on both of the sides are going to cancel out. So we're just left with x squared plus x equals 0. This is going to factor into x times x plus 1 equal to 0. And we get two solutions, x equals 0 or x equals -1. Now we need to make sure that these work. So if we plug x equals 0 into our original equation, 0 plus 2 is 2, so there's no issue there. 1 minus 0 is 1, so there's no issue there. Again, we're looking for negative numbers when we plug this in. If we take -1 and we plug it in, -1 plus 2 is 1, so there's no issue there. And 1 minus -1 is 2. So again, there's no issue there. So it's fine to have a negative solution, but you need to make sure that when you plug it in, you don't have the logarithm of a negative number. That is what causes issues. So both of these solutions are actually in the domain. All right, now let's take a look at this one. So we have 3 to the x power equals 7. So anytime you have an x in your exponent, what you're going to need to do is either to take log or natural log of both sides in order to be able to bring it down. So we've taken ln of both sides, but it really doesn't matter what you do. So we have ln of 3 to the x power equals ln of 7. Now, since we have an x in our exponent, now what we can do is we can rewrite it as a factor. So we've taken our x and we've stuck it out front, so we're left with x times ln of 3 equals ln of 7. And then in order to get x by itself, this is x times ln of 3, so we just have to divide both sides by ln of 3. So we're left with x equals ln of 7 over ln of 3. This would be our exact solution, and then if you want an approximate solution, you'd need to actually put this in your calculator. Make sure that when you enter this in, you have ln of 7, and then you close a parenthesis if it opened it, and then do divided by ln of 3. And you'll end up with an approximate solution of 1.771. Now you'll know if you got this right by plugging it back in here. So if you do 3 to the 1.771 power, you're going to get something really, really close to 7. It's not going to be exact because of the fact that we rounded this, so this is not exact either, but it's going to be pretty darn close. All right, now let's take a look at this one here. So we have 5 times 2 to the x power equals 3. So what we need to do is we need to get this exponent part by itself. So first we need to divide both sides by 5 so that our 2 to the x is all alone. So we get 2 to the x power equals 3/5. And then again we take natural log or log of both sides so that we're able to move x out of our exponent. So we take ln of both sides, so we have ln of 2 to the x power equals ln of 3/5. And then we take our x and we stick it out front. So we have x times ln of 2 equals ln of 3/5. And then we divide both sides by ln of 2 so that x will be alone. So our exact solution would be ln of 3/5 over ln of 2. But our approximate solution, if we plug this into our calculator, would be -0.737. And again, you can know if you got this correct by taking this, plugging it in for x, and making sure that it works. And this one, again, when you do 5 times 2 to the -0.737 power, you're going to get some number that's pretty close to 3. Again, it's not going to be exact since this one was rounded. I'm going to skip through this one. If you're a little stuck on your exponential equations, I would suggest going back and reviewing this, but I want to make sure that we get to this last couple of topics, which are compound interest and solving equations. So if you're stuck at all on the exponential equations, I would make sure that you go back and rewatch that entire video lecture. So let's take a look at compound interest. So compound interest follows this formula here. So amount A after t years due to a principal P invested at an annual interest rate of R compounded n times per year is going to be given by this equation here, where we have A equals P times the quantity 1 plus R over n to the nt power. So let's take a look at a couple of examples here to make sure that it makes sense. So we have $1,000, that's going to be our principal. We have a rate of 10%, so we're going to rewrite that as 0.10. Now we're going to do this for compounded annually, semi-annually, quarter, monthly, and daily, and we're going to do it for just 1 year, which simplifies things a little bit. So in this case, all we have to do is take our principal, which is our $1,000, and multiply by 1 plus, if we're just doing compounded once a year, we're going to just have R over 1. which is just going to be 0.10 since r is 0.10. And then our time, all of these are just going to be to the first power here, okay, multiplied by n. So in this case, since n is 1 and time is also 1, this is just to the first power. So if you do this in your calculator, you're going to get $1,100 as your new balance after 1 year. Now, if you have something that's semi-annually compounding, it means that twice a year, your balance is reconfigured. So what you need to do is you need to do something very similar, but instead of just having r, you have r over n. So in this case, we have r over 2. And then instead of just raising it to the first power, we raise it to the n times t power. N is 2, time is still 1 year, so this is just going to be squared. So when you actually take your rate and you divide it by 2, you get 0.05. So you have 1,000 times the quantity 1 plus 0.05 squared. And if you do this in your calculator, you're going to get $1,102.50. So if you notice, you have a little bit more money than you did when it was only annually compounding. So if you're putting money into an account, you want it to be compounded as frequently as possible in order to end up with the most money. So I want you guys to go ahead and try n equals 4 and n equals 12 and make sure that you're able to get these two solutions. And then you could try n equals 65 as well, but if you understand the others, then that one will make sense too. So let me give you a minute to double check that you're able to get these to work. So keep in mind when you have quarterly compounding, that's going to be 4 times a year. So if you take your rate and you divide by 4, you're going to get 0.025, and then you're going to raise it to the 4th power because it's 4 times a year. Same idea with the 12th power. Because you have monthly compounding, n is going to be equal to 12. So you're going to take your rate, which is your 0.10, and you're going to divide it by 12. You're going to add that to 1, raise it to the 12th power, and then multiply by your 1,000. Each time you're going to notice you get a little bit more money. And then for n equals 65, you take your rate, you divide it by 365, since it's daily compounding, which is 365 times a year. You add that to your 1, raise it to the 365th power, and then multiply by 1,000, and you should get $1,105.16. Now the last thing that I want to talk about today is solving linear equations. So let's take a look at one where it's just 2 equations with 2 variables, and then we're going to take a look at 3 equations and 3 variables. So if we have 2x plus 3y equals -1 and 2x minus y equals 3, what we want to do is we want to use elimination so that one of our variables is going to be the additive inverse of the other, meaning that we would have either 2x and -2x, or we'd have 3y and -3y, or something like that. So it looks like what they've chosen to do is to multiply this second equation, multiply everything by 3. So 2x plus 3y equals -1 has just been left alone. That's my first equation. And then I take my second equation and I multiply everything by 3. And when I do that, I get 6x minus 3y equals 9. Now you have to make sure that you multiply every single piece by 3. Now that I have this equation, this first one, and the second equation here, you'll notice I have a positive 3y and a negative 3y, so those are going to go away just like I'd like. So I'm left with 8x, because that's 2x plus 6x, equals 8, because I have -1 plus 9. So if I solve this, I just get x equals 1, and that's my solution for x. Now, all you have to do at this point is just to substitute back to find y. So you just pick one of your original equations. It looks like they picked this one here. So they have 2x minus y equals 3. And all we've done is we've just plugged 1 in for x. So we have 2 times 1 minus y equals 3. And then we just solve this. And if you solve this very carefully, you're going to get y equals -1. So our solution that we found would be x equals 1, y equals -1. And then what they've done is they've checked it by just plugging them into the original. So the nice thing about this is you'll always know whether you got them correct because you can always plug it back into the original. So you plug it into the first equation and you plug it into the second equation and you make sure that they work. And these will both work. So my solution that I would write would be 1, -1 because it's always x and then y. So x equals 1, y equals -1. Let's skip this movie theater ticket sales because I want to make sure we get to one with 3 variables. This one you could find in the last video where I talked about linear equations. So if you want a little bit extra review on that, you could go back to that one. But let's go ahead and do this one here where we're solving a system of 3 linear equations with 3 variables. So what you're going to do is you're going to use the method of elimination that we just went through, but we're going to have to do it a couple of times. So if we take a look at our equations here, what we want to do is we want to try to eliminate the same variable 2 different times. So if we take a look at this one, it looks like what we're going to do is we're going to take the first equation and we're going to multiply it. Or wait, no, it looks like we're leaving that one alone. Okay, we're going to take first equation and third equation. Oh, it looks like our connection was lost here. Hold on one second while I figure this out. So it looks like this is still working okay, but let's go through this example quickly here in case I get timed out. But what we're going to do is we're going to take this first equation and this third equation, and we're going to multiply the third equation by -2. And what this is going to allow us to do is to take the first and third equations together and eliminate these, okay? Because the x's are going to go away. So if we take this third equation and we multiply everything by -2, we're going to get -2x plus 4y minus 6z equals -14. And then we take the first equation and the third equation and we put them back together, and we're left with 5y minus 5z equals -10. Now, next to this equation, what I would suggest doing is that you go ahead and you put a little star next to this equation so that you don't lose it. And then what you're going to do is you have to use the second equation somehow, and what you'd like to do is you'd like to eliminate x again. Okay, so you're going to use the second equation and one of the other equations in order to eliminate x. And the easiest thing to do is going to be to take this third equation and the second equation. You're going to take the third equation and you're going to multiply everything by 3. And when you do that, you're going to be able to take second equation and the third equation together, and the x's are going to cancel again, just like we would like. So we have our second equation, which is -3x plus 2y minus 2z equals -10. And then we have our third equation, and we multiply everything by 3. And if we do that, we're left with 3x minus 6y plus 9z equals 21. And then we just add these two equations together, so we're left with -4y plus 7z equals 11. And then I would put a little star next to this equation as well. Now, once you have these two equations, they should have the same variables in them. If they don't, then it means that you did something incorrectly. So you should have y's and z's in both. And then what we're going to do is we're just going to stick them next to each other so we can figure out how to eliminate. So if we take this equation and we multiply everything by 4, and we take this bottom equation and we multiply everything by 5, you're going to have a 20y and a -20y, and then those are going to cancel. So we're going to take this first equation, multiply everything by 4, and we're left with 20y minus 20z equals -40. And then we take this bottom equation and multiply everything by 5, and we're left with -20y plus 35z equals 55. Then all we have to do is just put these together. So we get 15z equals 15, so we get z equals 1. And then all you need to do is you need to take this z equals 1 solution and you need to plug it back into one of your start equations. We had one where we had 5y minus 5z equals -10. That was one of our start equations. So we just have 5y minus 5 times z, which in this case is 1, equals -10. And we go ahead and solve this. We get y equals -1. I would make sure that as you find these solutions, you circle them on your paper because it gets a little bit messy. So we know z equals 1 and we know y equals -1. And then the last thing we want to do is just solve for x. So we just take one of our original equations. It looks like they took the last one here. So we have x minus 2y, which is y is -1, plus 3z, where z is 1, equals 7. And then we just have to solve this, and we get x equals 2. So our solution is going to be x equals 2, y equals -1, and z equals 1. And again, you can check this and make sure that you got it correct by plugging these into each of your 3 equations and making sure that they all work. And if you did it correctly, then that will be the case. So at this point, I want to ask if there are any questions on anything. I'd be happy to answer any questions if you have them. Okay, so it does not look like there are any questions. I want to wish you the best of luck on your Math 136 final. This will be the last video lecture for the semester, so thank you so much for joining and have a great rest of your semester.